Welcome back to the geotechnical seminar. And today it's our great honor to have Dr. Pooneh Maghoul being here. Her topic will be to work at digital twin for the permafrost management in the context of climate change. I will just read a few lines about Dr. Pooneh. She is an associate professor in the Department of Civil, Geological, and Mining Engineering in Polytechnique, Montreal. She holds a Master of Science and PhD from, very difficult for me to pronounce it, and maybe you can help me.
École Nationale des Ponts et Chaussées.
Okay,
in
so
Paris.
Yeah, so if we want to speak in English, probably it's Ponts Paris Tech, I guess.
Exactly. Or you can say Paris Institute of Technology.
Okay, got it. And she is an expert in the field of multi-scale mechanics for complex materials and processing, energy and environment, and biomechanics. Her research focuses primarily on the sustainable development by developing cutting-edge systems and methods related to the performance analysis of subsurface systems subject to complex loading within a multi-hazard context. And this includes infrastructure, which is resilient to climate change and geohazards on Earth and harsh environments in space, which is mainly low gravity conditions. And without further ado, Dr. Pooneh, you can take over.
Yeah, thank you very much. It's my honor to be today with you. Thank you very much for the invitation. I just go through my slides first. I have a brief introduction, and after I will switch to the main topic of this talk, which is toward a digital twin for permafrost management in the context of climate change. Yeah, this is my background. As you can see, as diverse as 3 continents. I got my bachelor degree at the University of Tehran in Iran, and after I moved to Paris in France to pursue my studies, I got my master degree and my PhD at Paris Institute of Technology, or the other name is École des Ponts Polytechnique. Then I moved to Quebec City in 2010, 2011. I did my postdoc at Laval University, and I worked with Hydro-Quebec on an energy-based project and a bit related to cold regions stuff. And after I moved to Montreal, I worked for 2 years in Montreal as a geotechnical project manager, and I taught at École Polytechnique Montréal and ETS, École de Technologie Supérieure. And in 2015, we moved to Winnipeg. I started my academic career at the University of Manitoba, and voila, in 2021, I'm again here in Montreal, and I am working at Polytechnique Montreal. Then if you look at this path, probably you imagine that I had to go to Pacific Ocean, but no, I just went back to Montreal. Then my diverse, background is also diverse my taste in food and in sport. I love many things from different, countries, and also I love sport, and I do lots of different, sports from soccer and even kickboxing. Then this is actually my professional background. As I told you, I am an associate prof of civil engineering at Polytechnique Montreal. Before that, I was at the University of Manitoba and worked as a geotechnical project manager and a sessional lecturer in Montreal. My research projects are broad, but mainly if I really want to describe it, it's everything around the concepts of poromechanics or mechanics of porous media. Then you know better than me that when we say porous media, it can be rock, it can be geomaterials, soils, it can be tissues, skins, and it can be placenta, and it can be everything, all the porous stuff that we have in this world, and even in the space. Then this is actually the overall research interest that I have. Then today I want to talk about the concept of digital twin for permafrost management. I think you are all in Canada, and you know better than me the conditions of northern infrastructure. Here you can see two probably usual pictures, images of northern infrastructure that unfortunately, because of the adverse effect of climate change, we can see uneven settlement conditions and etc. The other thing that we know is that permafrost is probably likely is one of the biggest the carbon reserve on our planet, and due to climate change and permafrost thaw, we have lots of CO2 and CH4 that which are released to the atmosphere. Then these concepts, they are probably the typical to our century, 21st century. And the problem is based on what we know, based on our experience, past experience, and based on what we have learned so far, what we have developed so far, and also the emerging technology that these days in other fields we use, and even in geotechnical engineering we use, how we can gather all of these topics, all of these areas together to develop a kind of holistic technology for permafrost management. Then this is the main topic of my research these days, just to see how we can deal with northern infrastructure, climate change, and CO2 or let's say gas à effet de serre or greenhouse gases to the atmosphere. I took this video from Brandon. Then this is actually the biggest problem we have related to permafrost and ice-rich permafrost. And as Brendan said, just imagine we have kind of infrastructure or a building or highway or runway sitting on top of this. Then the pictures that I just show you is actually related to this big deformation, huge deformation, or large deformation, if you want to speak from geotechnical point of view, related to the permafrost. And the other thing, as I told you, the time permafrost alters landscapes, threatens infrastructure built on it, such as roads, buildings, and pipelines. And the extent of that threat depends on permafrost characteristics, which can vary greatly even over small areas. Here you can see different types of permafrost we have: continuous, discontinuous, or sporadic, isolated permafrost. My background, actually, my PhD degree was on geotechnical earthquake engineering, seismic side effect. I had, during my PhD, my grad, schools, I had nothing to do with cold regions and permafrost. And my actually PhD was exactly on this locality. I mean, we have for example, different geological sediments. We have soft soils, and we have, let's say, dense soils, and we have topographic irregularities in a site, in a city, even within a city. And we wanted to study how these topographic irregularities and how these change in soil types can amplify or de-amplify the seismic site response. Then basically in our analysis in geotechnical earthquake engineering, in seismic site effect studies, this effect of locality, these effects are actually very important. And we could see, for example, the response of a building close to a valley can be amplified by the order of 3 to 6. And every time we have an earthquake, we observe actually the effect of site, or this locality on the seismic site response. To me, with this background, when I see these pictures, continuous, discontinuous, or isolated permafrost, this, isolated or dispersed patch of ice, to me, it's exactly similar to this seismic side effect concept. And how we can consider this, the discontinuity, this heterogeneity, in not seismic site response, because it is not the case, but in actually infrastructure response or permafrost deformation, or what we have as, you know, the uneven settlement that we can observe. Then to me, with that background, it is very important to have a platform, even within a village, even within a city, especially we have important infrastructure, critical infrastructure, how we can, based on our knowledge and our heritage in seismic site effect and geotechnical earthquake engineering, how we can reproduce this concept in the context of permafrost, to see actually the effect of locality on infrastructure movement and deformation. The other thing, it is related to, see something here, okay. It is about the effect of permafrost carbon feedback. I know that as a member of the Canadian Permafrost Association, this topic actually started, I think, since last year in 2021, we had a dialogue on this permafrost carbon feedback, which was greatly impressive, and I really appreciated this dialogue, just to guide us, direct us to go to this you know, direction and do research to understand better the mechanism of greenhouse gas emissions from the permafrost. And here in the box, you can see just some rough information. As you can see, cumulative permafrost emissions could reach 150 billion tons of carbon by the year 2100 without aggressive climate policies or climate change adaptation strategies. It seems a bit scary, even when we know that this amount is nearly half the world's remaining carbon budget, if we want to keep warming under 2 degrees, which is the limit set in international climate agreements. I don't know, these statements are exaggerated, or it's true, or if it's true, which is true actually, what is the weight of it? If, for example, 90% is correct, 50% is correct, then in terms of climate change adaptation, we have different scenarios, and it becomes very important actually to consider this in any types of probabilistic analysis, or as I told you, like city scale analysis or site scale analysis. Then here again, roughly some information about that the temperature rise in Arctic regions, it's approximately twice the rate as the entire globe. This is a phenomenon known as Arctic amplification, and it can cause lots of, you know, the climate, you know, the related hazards. And the other thing that in geotechnical earthquake engineering, especially with regards to northern infrastructure, I personally, every day, you know, every 2 days on social media, I see it is related to retrogressive tow slumps, which are defined as landslides caused by the melt of ground ice in permafrost. And billions of dollars of damage. And what happens in north, it will not stay in the north. We can see it in Vancouver, we can see it in Montreal, we can see it in Toronto and other regions. Then we really need to have a robust, you know, plan just to deal with this permafrost degradation due to climate change. The other thing that we hear these days a lot is that I was reviewing actually a grant a few days ago, not related to permafrost and not related really to my field of research. It was something about climate change. And, you know, it was written that the majority of problems we will see related to climate change, that would be in the mid-century. And it is, again, I totally agree with this comment. I actually didn't have any proof or any the article papers that prove actually my thought, but I was so happy to see this statement in that grant, because this is totally true. And what we see now, what we have learned from climate change impact, from permafrost degradation, I think we will be a bit probably shocked. Maybe it's again an exaggerated term, but I expect myself that within 10 years, 15 years, we will see lots of, the things and phenomena that we were even not supposed to see, or even we never thought actually about these problems. Then one of the things that I was thinking about, it was the differences between mitigation and adaptation. Then mitigation is just some probably kind of temporary solutions, how we can deal with, the type of the structure which is damaged. Then what solutions we can offer. But we have another term related to adaptation, resiliency. These are the terms that in civil engineering, in engineering total, in circular economy, in sustainable development, we hear a lot. The concept like adaptation, resiliency, and robustness, and these are actually the terms with very important meaning and philosophy. And we have to pay attention when we want to use them. Not to use them, but even in research development, I think in research design, it becomes very, very important. For example, the main question is how we can have a kind of climate change adaptation strategy that can work, let's say, until 2060, 70, and ideally 2100. And we don't know in 2014, 2050, what else we should expect. And what we have to actually, how we can deal with these things. I give you an example. The majority of models we have in permafrost engineering, it is started by a few scholars in your university of Alberta, at Polytechnique, Montreal. Then in the 80s, in the 90s, and even in the 20s, they continued and they started to develop advanced models just to see how permafrost reacts, how permafrost actually behave under climate change. And if we have, for example, temperature gradient, or we have a changing permafrost environment from geomechanical point of view, how we can deal with that. To me, when I see actually this literature, I feel that the philosophy behind those models are a bit different from the challenges that we are facing today. I give you an example. Probably in the 80s and 90s, we never had this intensity, in extreme events. I don't think that it was a problem. The majority of models that developed at that time, it was related to frost action. How we can model frost heave, how we can model thaw settlement. But what about the effect of extreme events on northern infrastructure, and even natural builds? We don't know. And I am sure that the model that we developed cannot actually answer these questions. Then it's very important that we see permafrost in the 21st century in its concept. And again, adaptation with future, it's something that we have to think what other loading conditions, what other temperature or thermal loading we can have. In addition to that, greenhouse gas emissions, and in the context, we have to see how we can learn from our heritage in permafrost engineering, and develop some strategies to answer the challenges we have with regard to permafrost in the 21st century. Then with that idea, I started working on this concept, digital twins technology, since 2019, 2018. It's actually quite recent that I started working on this topic. One of the reasons is I started my academic job in 2015, and I was on maternity leave right after, and I really started working on research development and research design since 2017. Then permafrost was one of my main topics, and people ask me why. I just told you my background was on geotechnical earthquake engineering, and There are actually two reasons. One of them, it's funny because Manitoba was the only province in Canada with almost zero seismicity. Then doing geotechnical earthquake engineering in non-seismic, province just motivated me to broaden a bit my research scopes. And I wanted actually as a young researcher, early career researcher, I just wanted to do something impactful. I don't want to say geotechnical earthquake engineering is not impactful. It is. It is great, and we have to do it because we still have lots of problems with regard to geotechnical earthquake engineering. But as I told you, as a young and early career researcher, I just wanted to develop something new, use emerging technologies, and work on something that can have real or tangible, the impact. And one of them was climate change, of course. Then I had all this, I started reading literature about the climate change, different reports, or again, heritage, past experiences, the models and everything. And I personally found lots of gaps in the literature in our way of thinking and seeing the problem. I started this research, and at the beginning, I never actually used these term digital twins. It's just recently I figured out that everything I do, it can be around a concept we call a digital twin, which is hopefully, unfortunately, not hopefully, fortunately, sorry, it is a trend these days in other fields of research, in mechanical engineering and in other actually fields. Digital twin is not new. Digital twin concept was developed firstly by NASA in the 70s. During the Apollo missions, they just wanted to have a robust simulator, just to imagine if they want to send a rocket ship or something to the space, how it behaves, under harsh conditions. Then we take this concept digital twin, as I told you, from the aerospace industry. And these days, again, it's a term that everyone tried to develop on different, in different applications. In smart cities, we hear a lot the concept of digital twin. In big data, everything that deal with IoT or sensors captures everything, then we try to relate it to digital twin. Applying digital twin to permafrost or to any geostructures, or even natural, let's say natural slopes. Applying this concept to geotechnical engineering, it's very tricky. Why? Not because of the sensors, not because of the remote sensing concept, just because of the complex behavior of geomaterials. And permafrost itself, to me, with a background in geomechanics and poromechanics, with that theoretical, background, I am so excited about it, not because it is permafrost and it's related to climate change, because intellectually speaking, it's one of the most complex geomaterials that can exist. It's a multi-phase system. We have a combination of water ice, it was a lunar application. They all the time use it, water ice content, unfrozen water content. We have a solid skeleton that can be of any type. We can have the presence of microbes, lots of, the microbial activities in it. We can have actually any kind of complex flow movement within the permafrost. Then it is very difficult from thermal, hydraulic, mechanical, and chemical perspective to study permafrost and predict its deformation under complex loading. Then here I had 4 scopes, how to characterize permafrost in real time, because it's still a biggest challenge, how we can merge different geophysical techniques or geomechanics concept to characterize permafrost in a non-invasive way, in a way that, these permafrosts, they're all in remote areas, and it's not easy to have access to it. Probably we can go there a few times per year, install our system, and through satellite and everything, we can receive the data and analyze the data. Then the philosophy behind this research was how we can characterize permafrost in a non-invasive way. The other one was how to monitor permafrost degradation. Then these days we use a lot remote sensing concept, the satellite images, how we can use AI and deep learning pattern recognition concept to take these images and analyze it. And we can in real time and in the future use AI to predict the ground deformation today and in the future. The other concept was how to predict the formation and dynamics of permafrost. I just told you, in my mind, the models we have, they are all great, no question on it. But if we want to study permafrost deformation, permafrost degradation, again, in the context of climate change in the 21st century, how we can use them? I give you an example. We have lots of these retrogressive tau slump. And are the existing models able to model it, to predict actually the initiation and development of tau slump? I don't know. It's something to study and develop, new concepts that can be really compatible with this 3D, deformation within permafrost. And if we put all these concepts together, how we can develop a disaster management tool. A disaster management tool in different scales. It can be city scale, tool, and it's very good. We have lots of northern facilities. We have lots of northern communities that unfortunately are affected by permafrost disappearance, permafrost degradation. And if we can develop something, a kind of asset management tool that can consider all these and at the same time can give us a kind of early detection system that we can say this community within 10 years, within 15 years, within, 20 years, this type of risk you may face. Then we can have enough time to think about the other adaptation strategies or have a plan to save our northern facilities and northern communities. Then the concept of digital twin, I told you, it is not new. It was developed originally by NASA, and the concept, I think you can see it in the term. We have a digital representation of a physical asset, process or system. Then it can be an airplane, it can be a permafrost site, it can be a building. It depends on what we want to study. We have a digital representation. In geotechnical engineering, we have lots of this digital representation. All the software we use from, GeoStudio, Plaxis, COMSOL, Abacus, whatever we use, it is actually kind of digital representation of the field. Again, we cannot really use all of them. It depends on the type of, the type of model we have, the type of boundary conditions we have, soil stratigraphy we have. It is a northern infrastructure or built, the environment. We deal with natural slopes, but everything we try to build, in a computer simulator, it can be kind of digital representation of a physical asset. The other thing, it's related to continuously updated. It is the second, actually, the pillar of this digital twin concept. We have to update everything. This is the problem we have in typical simulation or numerical simulation that we do in geotechnical earthquake engineering. Our models are rarely updated continuously. What we do ideally is that we take, we have 2, 3, 5, depending on the duration of the project. We have lots of sensors. We get information from these sensors. And ideally what we do is that we try to verify or validate our numerical model and get some results and do our engineering results. Unfortunately, what we do in our numerical simulation, it is not continuously updated. We stop it. We stop informing our model about the real conditions of the field. Then you can see that we can never be sure about the results we get in uncertain conditions such as climate change. The other thing is generates insights, predictability, and performance optimization. Based on this digital representation, continuously the updated, which is related to IoT system. When I say IoT, I mean Internet of Things, all information that we can have. For example, your phone, if you're close to a permafrost site and you send information about the condition of the site to my cloud and I can observe it, it can be part of my IoT system. Then sensors, that remote sensing technologies, everything that can give us information about real-time conditions, I put it in the category of IoT or Internet of Things concept. And what we can do with this information, as you can see, generate insight. Now we have this platform and what we can do with this platform. Then here what I define is actually based on this early warning system or disaster management tool. From this platform, we can get information and we can get insight and we can use it for decision making, for public policy, and for urban planning. Then the connection between this digital representation and the site or physical asset itself consists of the data that is transmitted back and forth between a physical object, that here is our permafrost site or northern infrastructure, and a digital twin. Then you see the concept, we have a digital, simulator representation, and we have a physical asset, which becomes a digital twin. Then just talked about the things or Internet of Things. Again, it's a concept which is very popular these days in the literature, mainly because of the concept of the smart cities and resiliency and all these fancy things that we have these days in the literature. Then it can be, as I told you, sensors, it can be your phone, it can be the satellite image, everything that we can use it just to transfer data, to transfer actually this information about the real conditions of the site to our digital representation or digital twin system. Then now what we can use this concept again to monitor a northern infrastructure. What you can see is a mining facility in the north. And basically we can have lots of, we can gather lots of information. Our past experience, we can have, we can actually install so many sensors around the site. And with those who have extensive experience in northern, regions, it is not really easy to continuously monitor the information. Personally, I had this experience. You try to, we have actually lots of, the clouds and repositories that put information, collect information in each the location, all the sensors, and they gather information. And every time I want to use this information to feed my AI simulator, I have lots of problems. First of all, are these data really viable? Did they really get information correctly? It's something that we don't know. We are never sure about it. And the other thing is actually the tempo in time and space discontinuity that we have. We cannot use actually this data for training purposes. you have a discontinuity, your AI training will not work. Then we are actually solicited, we are encouraged to go through the lots of climate models just to see how we can have at least a kind of continuous data to use it for training purposes. Okay, anyway, I go back to my northern facility. As I told you, we can have equipped with lots of fancy sensors that we can put around the infrastructure for monitoring purposes. The other thing can be drones, the application of drones, UAV, or we can even use satellite images. Then as I told you, the first step is real-time ground conditions monitoring. Then I applied two concepts on it. One of them is remote sensing monitoring. That what we try to do, this is actually close to Gillam in Manitoba. Then what we tried to do is we got all the pictures from past satellite images, and today with RadarSat and other platforms provided by the Canadian Space Agency, we have lots of information. Then through this pattern recognition, deep learning stuff, we try to detect this northern infrastructure from roads, from winter roads even. We can have an idea about the locations, and they change over the time that they have. Then based on this remote sensing, thermal imaging through UAV, the survey, we can develop this remote sensing monitoring to send to our digital twin this real-time ground conditions. The other thing that we tried to do is based on physics-based geophysics monitoring that I will focus after this slide on this aspect. We have some good results to show today, and it's as I told you how we can use non-invasive techniques by using these sensors, geophones around the infrastructure. Then we can have an idea in real time about the permafrost conditions, subsurface conditions. What's the change in ice? What's the change in unfrozen water content? And how permafrost actually change in terms of mechanical response. It is something that we actually have tried. We have been trying through this physics-based geophysics, geomechanics monitoring to answer. Then this part give us, as I told you, permafrost conditions in real time. The other aspect, as I told you, it is for prediction. And we want to connect real time to the future. Then what also we tried to do is related to this, it's not activated, sorry, let's go back here. It's just to see how we can develop, again, a kind of AI-powered prediction tool to predict the ground surface temperature from now to 2100. And this is just 5 degrees in a place in Yukon that I presented here. Then what you can see here is actually mean annual ground surface temperature. Then our plan is, and then I hope that by the end of the spring we can provide this information Canada-wide. That for each zone we can have a very good, I hope very good prediction tool with regards to the ground surface temperature, that you can use it, you can install, you can download actually the information instead of using N factor or the other, the maybe empirical techniques. Then this is a kind of AI-powered prediction tool that you can download it and you can use it in your numerical simulation when you have, an engineering design in northern regions. Then it can give you information. For now, our focus is really going from weekly to annually. And this is actually our resolution for now. But yeah, you can download this information wherever you are. We actually use lots of data informed information, sensors. But as I told you, there are lots of discontinuity in this data collection that unfortunately sometimes it is not really helpful. Then this is actually, as I told you, the second step to connect real time to the future. And the other thing is prediction of ground depth deformation from now to 2100 in the context of permafrost in the 21st century. I mean, if we have extreme events, if we have, with all these mitigation solutions that currently we have, as far as I understood, our main focus is to keep the ground frozen. Then basically, when we talk about deformation, we try to keep it frozen. I mean, we manage, we engineer the thermal, the profile of the ground. We don't really focus on mechanical deformation. And my biggest question was, if in 2030, these mitigation solutions will no longer actually applicable, how we can do engineering design? Then what we try to do is basically developing a model that can be able, based on, again, our heritage in permafrost engineering, develop those models and come up with a more holistic and comprehensive constitutive model and numerical simulation to be able to address the challenges with regard to permafrost engineering, to northern infrastructure and slopes. And the other thing, the fourth step of it, is the development of a disaster management tool, early warning system for the disasters in the future, communications with the stakeholders through floods, networks, apps. Again, now for everything we want to do buff, we go to our, what's the name of that, Google Play or everything, we download an applications and we use it. Then we can do it. It can be done with simply $10,000. We pay a developer to develop this application for you, and you can use it, as a kind of information platform. But if we want to do it, again, in the context of climate change, permafrost degradation is not linear. Then we have to just, in this third step, we have to develop something, a concept that permits us to predict the most probable moment of large deformation within the permafrost. I hope I can transfer the message correctly. I'm not comfortable with what I just said, but I want just to say that permafrost settlement, it's not like linear. It can actually at the beginning be kind of linear and slow, and after a few years it can become like exponential. Then in that disaster and early warning system, it is directly and closely connected to this third step, the green step, because through this numerical simulation for the future, we should be able to say, listen, now our deformation in 2022 is linear and it's slow, but in 2030, 2035, it becomes like exponential. And this is actually very important to be considered in any, the planning perspectives. That was actually the overall goal of this digital twin, different components of digital twin, different elements. And as I told you, for now, I have 2-3 slides to finish my presentation. I just want to focus on this one, physics-based geophysics monitoring. It was done by one of my PhD students who recently graduated. I hope that next time you will invite me again in the near future, and I will go through all of these, the scopes step by step, just to inform you about our progress. Then in that physics-based characterization permafrost, again, we had two scopes. One was at in the lab scale. If we have, for example, a kind of permafrost core, permafrost sample, how through that ultrasonic testing, which is non-invasive, we can bring this setup. I will show you later a video that you can see. It's a very compact, setup, and we got a grant from Research Manitoba for proof of concept and prototyping. Actually, this technology that we patented last year. We use this ultrasonic system. You can put the receiver along the sample or at the top, and you get this signal, then we developed a kind of geomechanics-based signal processing to determine many unknowns within the permafrost. Then this is the prototype that now that we have in the lab. This is the mold that we use. Then if you have a kind of degraded permafrost, slushy stuff, I think you will be able again to use this mold. And as I told you, the purpose is to get lots of information necessary for the design. One of them is on frozen water content, ice content, porosity. Eventually, if we have the presence of ice lances and what's the volume actually of these ice lances within the permafrost sample, and mechanical properties. I have a question here about, do you see using a model to predict methane release from permafrost degradation? It is something that Dr. Rick, we are trying to develop, and we go through okay, I have another question. I will answer it later. And we go through what I wanted to say. Through the mechanical actually properties. I will answer this question next slide. Sorry for that. Then here in the lab scale, as I told you, to get physical and mechanical properties. After that, we tried. This is actually a solver. I just wanted to say that it's based on a spectral element method. It's not finite element method. We just have 2 points in our solver. Then you can get information, and quickly within 1 second you can have your answer. These are the physical properties, mechanical properties of your sample. The other thing that is related to Dr. Rick's question, it is in the field scale. Is that you have a huge northern infrastructure, or let's say natural slope, and you want to monitor it. Then again, from geophysical point of view, again, there are lots of limitations with regard to ground monitoring in the context of permafrost, again, I want to say. And again, we tried to use seismic waves, surface waves, then we could detect the presence of 2 types of surface waves, rayleigh waves, which are sensitive to physical and mechanical properties of the soil. Then for the physical, we just again did, we developed geomechanics solver to go through our solver and repeat it to get again within each layer of permafrost, the presence of ice lances, the presence of ice, the presence of unfrozen water content. And the biggest advantage is that we give you the numbers, we give you the values. It's really kind of quantitative characterization tool, which is a great help actually for digital twin purposes, for permafrost management purposes. And the other thing, in addition to physical properties, it's mechanical properties. Then when I say mechanical properties here, I mean bulk modulus, shear modulus, basically everything within the elastic, properties. But at the same time, the other advantage is through these, mechanical properties, we can detect the layers which are sensitive to greenhouse gas emissions. Then it's very actually the mechanical properties of soil layers. If you have till, if you have clay, if you have frozen silt, if you have a mix of everything like till, peat, or the layers which are really rich in carbon in terms of mechanical properties are quite different, which helps us to at least detect it. If we can detect it, for example, we have a layer rich in carbon within, I don't know, the first 3 meters, 4 meters, then we can have an idea about it. And the question that I have in the chat, how we can use the model to predict methane release, I have actually ongoing research just to see, to study actually the mechanism of methane release from permafrost from poor scale to larger scale. Then for now, our model is not able to predict the amount of methane release, but at least what we can do today is that we can detect, the layers which are sensitive to this carbon and methane released to the atmosphere. Yeah, these are actually all these, inverse and inverse analysis, forward solver stuff that we developed just to be able to give the number of layers we have. Then the question that I have is how deep we can go. It really depends on the type of and intensity or magnitude of seismic excitation. For example, if you use blasting technique, we can go very deep. But if we use a kind of very small hammer to generate like a classical MASW survey, then we cannot really go very deep. Then depending on the seismic excitation that we have, we can determine actually the depth of our survey. It's something that we can control. It's not something impossible. And these are my stellar team. I am really grateful for their hard work, and they all work on different aspects of the 4 research scopes that I just presented you. I have a question, student, the monitoring and digital presentation for building. We should have made it digital. Yeah, I do it. Quick, the monitoring or remote sensing are expensive. Who is paying for this? Government? That is a very good question. For now, what we actually try to do is that we paid a company. I don't remember the name. I can send you later if you want. Sorry, because it was for 2 years ago. That they have lots of satellite images, high resolution images in Thompson, in Manitoba. Then yeah, we can get information. I think it was from 1995, 98, if I'm correct. I don't remember exactly. Sorry for that. That can actually provide us. The other thing that I saw 2 days ago is that Canadian Space Agency try to put all the information, I think for free for sure it's for free, that you can have access to satellite images, that we can use it. The other thing that my student Felipe actually done, I think he contacted European Space Agency because they have actually this platform, at least for what we develop. Now we are in the prototyping and development purposes. Then my main concern is not how much information we can get through the satellite images. But I am sure that within, I don't know, a few years, with all the stuff that Elon Musk is doing with its satellite and RadarSat that the Canadian Space Agency actually is using, with all the platforms that European Space Agency are provided, I think this should be actually our least concern. And about who founded it, it was actually, I initiated this project through a New Frontiers in Research Month grant that I received in 2019. The funding source, I didn't acknowledge them here, I'm sorry for that, but it's mainly from New Frontiers in Research Fund and my tax. Yes. When every time I use physics-based, I mean this multi-phase concept of permafrost. Then we have, as you said, I don't know Weddell zone for sure, but we can even have kind of saturated permafrost. Saturated in terms of still have unfrozen water content and ice content within permafrost. I mean, it is not unsaturated, but again, we can develop it for unsaturated permafrost too. Did I answer your question? These phases, yes, I consider rock interaction in the, yes, we define it. We have actually definition for effective stress for permafrost. Thank you very much, Lucas. Thank you. Yeah, then if you have any question, please go ahead. I'm here to answer your questions.
Thank you so much for the great presentation, Dr. Pooneh. Thank you for sharing your vision, plan, and research about the permafrost management in the context of climate change. And you are definitely welcome to come back to present more whenever you want.
Yes, please invite me. I have lots of things to share with you.
Yeah, you have a larger chunk of work and you only present focused on the physical-based modeling research today. And I think you already covered the questions from Dr. Chalatonic, Dr. Deng, and Dr. Hagi. And we still have 5 minutes, and you are more than welcome to ask questions from audience, please.
Just I want to say something to Dr. Amir about that effective stress in permafrost. You know, effective stress in permafrost, similar to unsaturated soil, it is something that it's still there are lots of researchers that work on the concept of effective stress in permafrost. Then in the third scope of our research, which is related to numerical analysis and constitutive modeling, we made some assumptions to take, you know, the type of effective stress that can make our development a bit easier. But you know, the definition, as I told you, the definition of effective stress, it's similar to unsaturated soil. There are lots of, you know, the different theories how we can define it.
So I have one question here. Someone directed to me, to my chat. So it's from El Landrepar. Hi, very nice presentation from Dr. Maghoul. I have a more wide researching comment and question. Having practiced in the consulting industry for a few years now and having a keen interest in resilience of infrastructures, I find it hard to find good resources that I can apply to providing solutions to clients that go beyond policy making and academic research. Can you comment on the state of applied geotechnical resources available at the moment for practicing engineering consultants? As a follow-up question, what do you think of the state of the geotechnical community efforts with regards to resilience and climate change? For example, would the CFEM be due for some updates?
Thank you very much for your question. Actually, what you asked is actually my question too, my concerns too. That's why it motivated me to work on this topic. I totally agree with you about you know, climate policy. And as an engineer or researcher, when we try to understand the concepts and use it in our design, sometimes it becomes a bit tricky. I mean, it's always difficult to translate science to policy, but from a research point of view, I found that it is much more difficult to translate policy to science. The only source, to be honest with you, that I know about the concept of resiliency with regards to northern infrastructure is the work done by Dr. Guy Doré at Laval University. This is actually my Bible. Is every time I want to understand the concept, I actually go and dig into it. And to be honest, I don't have a clear answer to you because it is my question too. And I try to understand it and I try to actually develop the concepts. Because, you know, the definition of resiliency, I don't have the chart to show you in my presentation, unfortunately. But I can go there just to, here, when I say early warning system for the disasters in future, then resiliency is the ability of the infrastructure to bounce back, right? But if we, for example, we have it again in the context of permafrost degradation, we go to a state that permafrost is degrading significantly, intensely, and the deformation of infrastructure is in a way that we cannot prevent it anymore. We really need to be cautious about the thresholds we define and the exact meaning of each term we use. Robustness, resiliency, performance, they are very delicate terms. But as I told you, the ability of the system to bounce back from you know, a disaster, it is something that actually I am working on it and I have no clear answer to it for now.
Great. I saw Dr. Chalatonic is
well,
online.
No, it was just a quick comment to the last question, Dr. Maghoul, was that the CFEM is actually under a complete revision at the moment, right? there is a committee, and I think they're nearing completion of a completely revised.
I was part of that committee too with regard to permafrost. Yeah.
So you know, I suspect that you'll see a lot from a consulting state of practice kind of point of view. The CFEM updates will be, as I understand it, quite substantive. So
that's true.
You know,
but
technically,
sorry.
I wanted to ask a question. Is that, you know, buried in a lot of this stuff and a lot of things we do in that subsurface characterization has to do with the non-uniqueness. So when you get a multi-phase system, especially as complex as permafrost, because you now have solid elements, you know, you just don't have sand grains per se. You have pore space materials that actually have a stiffness characteristic and unfrozen water contents. What's your sense of how to unravel the non-uniqueness of your inversion?
I totally understand your the difficulties that you have had, because I've had too. You know, geophysics is the kind of black box. We never know what's going on. Then,
well, black box or black magic. One of
exactly. And in conventional, you know, techniques, at least I'm focusing on seismic survey because I know better the concepts. We have lots of assumptions, let's say, just to try to reduce this non-uniqueness in our solution. The other technique that they use from mostly research point of view is they use joint technique. They use seismic, they use another technique, then from one technique they get information and they fit, you know, the other technique through that. Then they use this joint technique in inverse, you know, algorithm that helps reduce the uncertainties. What we did actually in this research, we didn't use joint technique. What we did basically, it is through geomechanics. And when I say through geomechanics, is that here, as I showed you, we detect the presence of two, different types of Rayleigh waves, surface waves, and which actually each wave is sensitive to a set of parameters. We did lots of, you know, development just to understand the sensitivity of these waves to mechanical properties, to physical properties. And we were lucky because we could, at the end of the day, find a solution for that. Just by reducing and detecting new surface waves, which are generated just because of the multi-phase nature of permafrost. For example, we cannot see this type of survey waves in unfrozen soil because these waves are through interaction between different phases at pore scale that cause, you know, this distinction. It was actually the solution that we provided, and we had actually a little bit problem with that, non-uniqueness of solutions. But again, because it was based on this distinction between different type of surface waves, we could really reduce, you know, the problem we had.
I mean, it is well, as you know, it was kind of a loaded question because I have actually seen, right, we saw some of that work, one of your PhD students, but it is really intriguing because it's a different approach, because something as simple as Gassman's equation that will make some certain assumptions about dry and saturated bulk modulus and independence of shear modulus from pore fluids. You know, you're in this class of materials, you can't even do that, because shear modulus, now you've got frozen water, and even, you know, and unfrozen water and frozen water sitting in a pore space that makes even shear modulus a very complex material to interpret, right? So
that's true.
It's very nice.
Our model is not based on that rock physics concepts. You know? We just try to go through that multi-physics geomechanics stuff and use signals to interpret our solver. That helped us a bit to reduce the, you know, these assumptions that we have in rock physics models.
Nice. Yeah, very good.
Thank you.
So Dr. Hagi also online. And do you have any questions, follow up to questions?
Hi, Dr. Maghoul. Thanks for the great presentation. Yeah. Following my question about the effective stress. So you said that there are some definitions. Are we talking about like Bishop's effective stress, those functions that you consider all the phases, and then
Exactly, but you know, in the context of unsaturated soil or permafrost engineering, the definitions are a bit different. We don't have that Bishop the soil effective stress anymore. For example, what they define is going through not effective stress, but they define net stress and related to water degree of saturation, ice, the saturation degree. With some coefficients, they try to define the concept of effective stress.
Yeah. Thank you. That's great. A great research. Thanks.
Thank you very much. My pleasure.
Due to the time limitation, it's already 6 minutes past 1. And actually, I want to ask a question, but I think due to time, maybe it's going to be very quick. What's going to be your go-to choice for the prediction for the ground deformation in terms of the thermal hydromechanical finite animal modeling?
For prediction, you mean?
Yes, prediction of the ground deformation.
Our strategy, exactly. Our strategy for now is that through that first step, I mean real-time monitoring, we can define the initial conditions of the ground. And through this AI-powered prediction tool, we define our boundary conditions at the ground surface. And we just run our THM modeling, the analysis, and we can have an understanding about the deformation in the future. But the main feature of what we do in our numerical finite element analysis is the power of our constitutive model that we have been developing, which is able to detect, to consider the effect of thermal loading rate on permafrost degradation. Then through that, the constitutive model, we think that we will be able to detect even the initiation of tau slump.
Thank you so much.
My pleasure.
Yeah, we will be really glad to invite you back to present maybe the later half about the prediction of the ground deformation and disaster management tool in the future. And thank you so much for everyone attending this seminar. Just a short announcement before the end of the seminar. We are going to hold another guest from KCB, Dr. Hossein Ronani, to talk about the stability analysis of the slopes, dams, and open pits. And if you have any questions for Dr. Pooneh, you're more than welcome to send her an email. And thank you so much for attending. See you next week.
Thank you very much. Thank you, my pleasure. Thanks for your time.